Pardon? Milk. Huh? Milk tea. Milk.
There's a specific brand called Hagoromo.
Hagoromo.
Is there in Moscow?
No, no. I shall bring it from Japan. Hagoromo. Yeah. I will bring Hagoromo choke. No, it doesn't matter. Yeah, it's.
It's hard to use for me.
Mm-hmm. 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 Okay, so today I hope that I shall finish the story on the monodromy representation of hypergeometric functions in terms of by means of Merrin-Barnes integrals. So we introduced two types of, first of all, two types of integrand functions, say meromorphic functions. Minus z to the power s, and also another one, gamma 1 minus gamma. Maybe it's reasonable to take parentheses here, minus s, and divided by gamma 1 plus s. It must be 1 s, gamma 1 plus s, minus z to the power s. So these and this one, Hs, is Gs times some periodic function phi s equals phi s. Periodic. More precisely, it is written as expressed by a ratio to sine, sinus. Sine function phi s. I think that times, yeah, this one is sine sine pi s over sine pi s plus gamma. Yeah. So that is say, and we shall consider two types of series and neighborhood of z equals 0. That is say, c minus infinity, c plus infinity. We consider this integration path on the s-plane. And so that together, so this integration path, c minus infinity, c plus infinity, and the gamma factor has zeros, poles at positive, non-negative integers. Yeah? So GS poles of GS, and poles of GS has two types of. One tending to positive real part, yes, increasing sequence of poles with increasing of positive, we say non-negative real part, and this one is negative real part. Oh, then alpha beta specifically we can consider as rational numbers if it is we are treating the period of algebraic curve. So we have this, and so this is the situation, and so we have GS, GSDS, GSDS. Say HS, the say poles of HS is somehow 1 minus gamma. Somewhere here, maybe it's a rational number, 1 minus gamma, and 1 minus gamma plus 1, and so on. So it's, in fact, there is no specific restriction on gamma, but for the sake of simplicity, you can imagine that gamma, 1 minus gamma is somehow located on the right-hand side of this integration path. If necessary, if 1 minus gamma is read smaller than C, in fact, you can deform this integration path homologous in a homologous manner, so that this factor also has. So maybe I need to stress that both of them. These are also poles GS and HS, both of them. Yeah. Okay, so this one is. These are the poles of HS. So this one is. These are the poles of GS, and these is also poles of GS. Yes, GS. Okay, so and we have we can interpret this integral in different ways, so that depending on the choice of poles, which kind of poles you choose, you collect. So if I collect pole, consider summation of residues along these positive integers, then it will be a summation of residue at S GS, 2 pi I maybe, 2 pi times, no, there is no residue, say M. ds. Simply it's a residue of this meromorphic function that can be expressed concretely gamma function, and we saw that this was hypergeometric series up to some constant multiplication, hypergeometric series expressed in terms of Pochhammer symbols. Pochhammer symbols. So this is, if this is a convergent series, convergent in one, smaller one, then the same thing is valid for, in fact, in this case, I need to take 1 minus gamma plus m. S equals, sorry, maybe S equals m. S equals 1 minus gamma plus S of HS. We have already seen that really these two different series. So this one also is convergent in neighborhood of Z. Local solution. Two hypergeometric functions. So both of them are satisfy hypergeometric. Both of them are these are bases of base over C of solution space to the hypergeometric equation. That is theta s theta s plus gamma minus 1. Which one was S? Yeah, S times this minus. Sorry. Z. So function uz equals 0. Isn't it? Theta z, z times ddz. I think that it's correct. Once again, no. Contrary. So that okay. Y at infinity I have, yes, at 0 I have characteristic exponents 0 and 1 minus gamma, yeah, because at 0 there is a hypergeometric series that is holomorphic. Yeah, that is. So this is always up to. This is so every uz can be expressed locally in this inside an open disk as a linear combination of these series. That can be expressed as a summation residues of these. And what is remarkable this, this fact will be quite important. So GS, so this equation, maybe, this equation is equivalent to the following difference equation. What is GS plus 1? This is GS, yeah, GS plus 1 is times something times GS. There's a rational function that. So gamma factor, gamma alpha plus S plus 1, so gamma, of course, alpha plus 1, S plus 1, it is, of course, gamma alpha plus S times alpha plus S, isn't it? And for beta also. So I have alpha plus S, beta plus S, and then gamma minus S minus 1 here. So I have S minus 1. So, gamma also the same thing. Yeah. Minus 1. Then I have minus S minus 1 equals gamma minus S, isn't it? Yeah, that is, say, gamma minus S minus 1 is minus S minus 1 times this, and still I need to take into account the ratio minus Z. So I think that's correct, isn't it? I think that's correct. Yeah, so that is, say, minus, why there's minus? Because of this, in fact. These seemingly, how to say, ignorant signs, etc. play has something behind, yeah. That can be generalized further. Yeah, so I have this kind of relation. That is, say, this is meromorphic function, meromorphic function, but so-called this kind of contiguity relation. In literature, it is called contiguity relation. Or recurrence relation. Well, maybe contiguity is more, or simply it's a recurrence relation. Recurrence relation more general setting. Contiguity is somehow specific words for in the hypergeometric world. So this one is a rational function in S with parameter Z. Okay. And this fact, this fact, HS. HS also as HS equals GS times this periodic function, we see that HS plus 1 equals also RS times HS. That's all. It's evident. HS plus 1 is so. So HS also, GS and HS, both of them are solutions to the difference equation that is, say, something, okay, Ks equals Rs, s plus 1 equals Rs, rational function, times Ks. K, I denoted by Ks, so this unknown function to be found. Of course, the sum of these, GS and HS, or in fact, KS can be must be presented as summation of with C coefficients of these two functions, two meromorphic functions, as we have rank 2 differential equation, that is rank 2 differential equation. So this is a small remark. Going further, now, so today's aim is to get global monodromy representation of these integrals, these analytic continuation of this, this locally defined holomorphic functions. So these were convergent in Z and unit disk, open unit disk. But as we have seen that if we deform this, where is it? If we deform this integration path in a homologous manner, so we deformed this. Let us consider first the analytic continuation of this holomorphic function inside, and what happens if that goes to infinity? Yeah. To do this, we did this kind of procedure to deform, homologously deform. Homologous deformation must ensure the fact that this integrand, imaginary, so GS tends to 0 exponentially. So something like that. So it is e to the power minus delta of some imaginary part of S. Imaginary part of S and so on. We had this kind of estimation after studying theorem and studying, say, plus specific character of a gamma function. Yeah, quite precise version of studying theorem. We did it. So at the infinity, so these and GS and HS, both of them, decreases exponentially. Yeah, as imaginary part increases. So the modulus of that is, say, we can somehow we have no obstacle to deform this integration path without changing the value somehow. That it is legitimate to make this deformation. Yeah. So the first we gather this First intuition pass as this, and we gather it like this. And these were summation of minus residues, isn't it? So these are of S equals residue S equals M of GS. So now, if we deform path so that to gather residues at negative, or negatively oriented or somehow directed sequence of poles, we get a series that is convergent in 1 over z. So we have GS will be this integral. Okay, this first integral, maybe I can write GGH. G integral allows us interpretation as a summation of these poles, but positive direction. Residue is a positive. That is, say, the same integral summation of m infinity residue of minus s equals minus alpha minus m GS. Yeah, okay. Plus residue at s equals minus beta minus m of GS. Okay. And for H also, the story is completely parallel. Maybe so. Let us recall. So what is these? The GS residues are of GS S equals minus alpha minus m. That is, say, it is of course m factorial over 1 minus 1 to the power m. So the first factor is. Then later these are holomorphic. These are holomorphic at we assume that they don't coincide, alpha, beta, and zeros. They don't coincide, yeah. So the difference. So the remaining factor is holomorphic at s equals minus alpha minus m. So we can simply put the value of these coefficients. Yes, gamma beta minus alpha minus m, isn't it? Yeah. Is alpha plus m and gamma minus alpha minus m. Isn't it? Yeah, and minus z to the power minus alpha minus m. Okay. So that is, say, it can be factored out. You see that minus 1 to the power m cancelled, so only positive. And you see that this is z to the power minus alpha times some holomorphic function in 1 over z. 1 plus a. Non-zero constant, I don't know how to say, C0 So this is the characteristic exponent of this. So rather monodromy is governed by of this function is governed by this exponent. So if 1 over z okay, the second part, the absolute as parallel manner, so now I take s equals here this. So alpha minus beta minus m gamma of so minus s beta plus m over gamma small gamma minus beta minus m minus z to the power minus beta minus m. Okay, so this is z minus beta times c0 say tilde plus holomorphic n 1 over z. So this is G, the first, if you want, it is analytic continuation Gauss hypergeometric series, yeah, the classical one, up to some constant factor, yeah, that can express by means of these two hypergeometric series. Evidently, these are hypergeometric series, but in variable 1 over z. 1 over z. So these are convergent. In fact, convergence by D'Alembert test, you see immediately the radius convergence is 1, and you see this. So this is H, the G, the first one, and the second one, H, is also completely parallel in a parallel manner. So H also has it's a summation of S equals minus alpha minus m of HS, sorry, HS plus yeah, and the result is somehow quite parallel, but the difference is, well, difference is of course the coefficients of linear combination. So we have two series here. That is z to the power minus alpha times some holomorphic at infinity function, and z to the minus beta times, and this one also is linear combination of these two, but the coefficients, of course, different, so because these are somehow linearly independent solutions to hypergeometric equation. Yeah, that's the and okay. So I forgot to denote this. I take the notation G1. What is this? Yes. Let me denote it by G1Z. This means known by G2, yes, G2Z. Not so. And both of them are some linear combination of. Let us, so, to be precise, let us consider G infinity. Consider two solutions. Consider solutions. Got hypergeometric equation. This equation. Series solutions. So, to talk about the coefficients of linear combination, I need to somehow fix, somehow normalize this solution. These are everything. So, T infinity Z beta Z minus beta, but 1, it becomes from it's a kind of normalization. So, in fact, here, C0 is, what is this? C0 is, if I put m equals 0, then it is gamma, C0 is, I think that's gamma alpha, gamma beta minus alpha. I put m equals 0. I put m equals 0 and get minus 1 e to the power, this one I have, minus pi I alpha, and divided by gamma minus alpha, this kind of thing. So m 0, so it is 1. Okay. So in fact, here C0 was something like this. Yeah. So I put m equals 0. And calculate concretely, you can calculate concretely C0. Yeah. But instead of treating this kind of series that begins with somehow residue of s equals minus alpha of this meromorphic function, yeah, let us consider simply this kind of. Then we get the relation. The following relation, that's the normalization solution. Say main lemma to get the monodromy representation, global monodromy representation. That's our aim. Is the following connection relation, connection matrix. G1. So what is G1Z? G1Z, in fact, this is capital G1Z is essentially this one. Yeah. Huh? Analytic continuation of this, so holomorphic in unit disk, function homomorphic in unit disk. It's analytic continuation to infinity. That is, it is exactly capital G1Z. So capital G1Z and capital G2Z admits both local, so Z equals near 0 interpretation and the infinity interpretation. And here you see expression of this function asymptotic, so expansion near Z equals infinity. Yeah. Now, so in making use of this situation, we write down the relation between two types of solution bases. And this can be I explained this, so I need to see some irregularity. It's a 2 times 2 matrix, of course. A bit long. Well, simply it's a shift of everything I shift by 1 minus gamma. Okay, so I have 2 times 2 matrix, and with C, so what is C? C lambda mu nu. So it depends on three parameters. 3 parameters. Now, first of all, let us see how it is constructed. This parameter set. So alpha beta, first alpha and beta change, yeah. And the second one is add every parameter to every parameter. I add 1 minus gamma. 1 minus gamma. In fact, I have 1 here. Maybe it's better to here 1, and so 1 added by 1 minus gamma with 2 minus gamma, and the gamma added by 1 minus gamma will be 1. So 1 in this notation we ignore, so we don't see it. But this is somehow it is constructed. These coefficients are constructed. These transition matrix. Where this notation is where C lambda mu nu depends on 3 parameters. That is e to the power minus pi I lambda times gamma nu so this is so the first one C alpha beta gamma means C e to the power minus I alpha gamma of small gamma and gamma of beta minus alpha and gamma of beta and times gamma of gamma minus alpha. So something similar. Do I have gamma minus alpha? Yeah, this is something similar. Some gamma. Yeah. So this is somehow what I calculated before. Yeah, this is. Okay, so this is a kind of base change matrix. Base change matrix. I will explain it later. That how to calculate this base change matrix. Yeah. So that I denote by P passage. Let me denote by this equals P passage from one basis to another. So this basis to this basis, or to in the universe. Roughly speaking, this is this kind of somehow classical choice of solution basis in the theory of ordinary differential equation. These G infinity, these are is a classical one. And this one is obtained as analytic continuation Merin-Barnes integral. This, okay. So this is Merin-Barnes basis. So this is somehow OD theory basis. So I will explain that later. To the moment, it's enough. First of all, we shall establish our main result. Our main result. What in fact, how to get this global monotone representation of hypergeometric functions, rather with this basis or this basis, yeah. So and the advantage to use this basis to is the fact that it is extremely easy to calculate monodromy at z equals infinity with respect to this basis. So our aim is always in on S space PS. Sorry, Z1. There are three so these functions, hypergeometric functions, are living on a covering over P1 minus 3 points. And we need to calculate. So the monodromy representation is, by definition, is analytic continuation of these along these three paths. But we said that as the composition of three of them will give rise to an identity element in pi 1. So it is enough to consider this and this. This one this, or this one this. So now let us consider this and this. L0 and L infinity. So we understand P1 minus 3 points, some fixed point, as a group generated by two generators, L0 loop and L infinity loop. And then later we get L1 loop as a result of composition of these two. Why? Because, so to do this, let us begin by this, the monodromy along this path, this loop to study. And this is quite easily described in terms of these so classical OD bases, because as you see immediately that the action it will be simply e to the power minus or plus alpha. So 1 over z. Now we our 1 over z power alpha. 1 over z is our local coordinate. Local coordinate of this. Yeah. So that is say it is e to the power alpha. So e to the in a positive sense, yeah. And in a similar manner, it is also so very simple diagonal matrix we have with respect to this space. If I get this, okay, and now how about, yeah, that is say L infinity of G1 and GS, G1, G2, with respect to these bases, Merrin-Barnes bases, Merrin-Barnes bases. That is a analytic continuation monodromy around z equals the infinity of Merrin-Barnes integrals, yeah, is expressed as, of course, first I express G1, G2, P inverse, isn't it? Yeah. So to get this basis and multiply by and times P, conjugate. By conjugation I get this monodromy around z equals infinity of this Mellin-Barnes okay, at infinity we got it. And how about z equals 0, around z equals 0? But it is also very easy because we know this. So upper, the first line of the upper blackboard represent capital G1 Z. Evidently, it has where did it write? Z to the power r. It is holomorphic, so there is no monodromy. So if that makes turn around 0, it doesn't change. Yeah. The second one does have. Yeah. Second one does have because it is. So it is z to the power 1 minus gamma times some holomorphic function at 0, around 0. Okay. This series. That is, say, monodromy around z equals 0 okay, G1, G2 simply it's 1, 0, 0 e to the power 1 minus gamma. E to the power minus gamma. G1, G2. So at 0, the monodromy representation is obtained quite easily for Mellin-Barnes. Mellin-Barnes basis, and so in this manner we got both of them. So we got the entire monodromy representation. So of course after some minus beta never. In fact, there are some non-resonant conditions that I need to impose. For example, these are gamma is not an interior and so on. Yeah. Otherwise, there may appear some Jordan cells and so on. But yeah. For simplicity, to have first idea about this, let us fix first. So non-resonant situation. That is say, we established now this theorem. The global monodromy representation of solution space of say hypergeometric functions has the following form generated by two So I denote it m0 equals with gamma. This was e to the power alpha 2 pi alpha 0 0 power beta p inverse. And m1 is so around and z equals 1, around z equals 1, the monodromy is obtained as m0 inverse monodromy around z equals 1, or yeah. And we see that, in fact, so we need to use these P matrix that I will explain why these P, this expression is valid to the moment we expect. Then eigenvalues. So eigenvalues of M1 is can be, so there is a, it's conjugate to a diagonal matrix with these entries. And this number, gamma minus beta minus alpha, quite an important number, is somehow characterization of behavior of hypergeometric function z equals 1. Yeah. In general, it is so. In fact, this is. In fact, this fact to get the monodromy around z equals 1, or it is, if you recall, the cycles, we had, so we got the almost the same result, the parallel result for monomer representation for cycles, or for Hama cycles we obtained it, which in fact we calculated for chains. Let us say we denoted former result was H0 transpose. We got we got these two matrices, in fact. By cycle method, or a cycle monodromy, we obtained this representation: 1 minus 1 plus E minus beta 0 E minus gamma. So you see that 1, of course, it's the eigenvalue is 1 and e to the power minus gamma. Of course, it is the same. as here. So these are, there must be base change H, and we calculated H1. What happens? Yes. Transpose equals 1 minus e to the power minus alpha that's so of diagonal part, and e to the power gamma minus beta minus alpha. That is. So this was the result. Yeah, here right there. That obtained by following. So the deformation of say den twist, say. Topological method. In fact, we did it. We did it by means of a kind of algebraic topology of change of cycles defined on a algebraic curve. Y to the power m equals xa 1 minus x to the power b, and 1 minus z x power c. And that when z goes to tends to 1, the integration will some integration cycle will vanish, and that causes monodrome. That was somehow the way how we calculated it. And we see that the same result. That is say, in fact, we have M. There is a transition matrix. Between these matrices, these monodromy representation. I denote it. Yes, T, M, J, infinity. There is a transition matrix. Transition matrix from here it is written in terms of cycles, or change. Here it is written in terms of integrals, so many bounds integrals. But there is a transition between this, and this is a great. If we can do it more in a more general setting, many of questions of algebraic geometry will be solved. So, if we can, we succeed too. And I propose to, I'm doing this, more higher dimensional and more complicated algebraic variety, depending on many parameters, maybe, but the model is here, That is to translate the question of monodromy of cycles to that of integrals, that of many bounds integrals written down in terms of gamma functions. In fact, this one is far easier to, in certain sense, to generalize than this one. Okay, so now at the end, I shall explain how to calculate this P matrix, passage matrix. This matrix. This C alpha beta alpha gamma. It is simply the comparison comparison of concrete calculation of Mellin-Barnes integral. Now maybe I can make some. I don't know whether how much there is no dentist or rather in algebraic geometry or singularity theory, Picard-Lefschetz formula, yeah. Kind of fundamental. So to calculate this, we essentially we did this kind of Picard-Lefschetz transformation. Yeah. But this one is very difficult to. It causes so much difficulties in to generalize. Higher dimensional, complicated. Algebraic varieties, yeah, to study the homology for higher dimensional algebraic varieties is quite difficult. But in toric setting, this formula or generalization of this formula give us the hope to get this kind of Picard-Lefschetz formula in terms of Mellin-Barnes integrals. Yeah. Then this is quite successful. Successful, I don't know. Yeah, this is people recognize this validity, the usefulness, and mirror symmetry. So this kind of category, vanishing cycle, monodromy vanishing cycles. Yeah, this is. So one hope is to attract to people from mirror symmetry but from A-side specialists. Here in Moscow, almost all of specialists are B, coherent sheaves specialists. Okay, so now let me pass to the explanation of this C. This formula. This is. So everything, of course, relies on this concrete residue calculation, but it is at 0, so I need to calculate the residues at this one, yeah, G H, only H remained, yeah, but that is the same. So G1 that is say maybe yes, I don't, maybe I write it so residues of without 2 pi I, let us equals minus G1 equals G1z is residue at alpha minus m of GS and m. Yes. Okay. So the it is enough. So the G infinity Z alpha, that is something that begins from 1 over Z minus alpha 1 plus one plus. So it's enough to calculate residue at 0 of these expressions to calculate these coefficients. Yeah? The very first one, that 1, isn't it? So residue of goes minus alpha of GS. What is this? It is e to the power minus pi alpha times gamma alpha. Yeah, that's all. That's all. That I wrote it before. Yeah. And wait a minute. No, it's not. Yeah, in any case, so this was GS also the same thing. What is this? Yeah. So this is e to the power minus pi I beta times gamma beta gamma alpha minus beta gamma minus beta. So this is SC is equal to C alpha beta. So e to the power minus gamma times gamma beta gamma minus alpha times residue at s equals 0 over GS. So in fact this is this is C alpha beta gamma, isn't it? So C alpha beta gamma, where is it? Yeah, C alpha beta gamma, I write it. It's on top, huh? Okay. Maybe not without going into the details, simply give you the idea how it is calculated. And this must be, so let me check. Gamma mu beta minus alpha gamma beta gamma minus alpha. Okay, that's it. Yes. This is the ratio that you need to calculate. And also, and also C beta alpha gamma times times, yeah, this is the same thing, residue of one. So this one begins from 1, yeah. No, 1 plus. So the others are also in a similar manner. And the best way to understand this is rather to write down, to add this 1 in fact, it's better to understand the Gauss hypergeometric function as depending on 4 parameters. 4 parameters, yeah. So it is like this. Isn't it? So in fact here we have one delta that we put at 1, and here in this expression also they're present is kind of in fact 1 that helps us to understand the structure of these coefficients, or rather to calculate this kind of coefficient for not only GX, but HS. HS. For HS, for everything HS, then the parameters, parameter shift, we shall take into account the parameter shift of the alpha, beta, gamma. Instead of 1, we shall take 1 minus gamma. Yeah, this is, so this corresponds to z to the power 0, z to the power 1 minus gamma. These are initial dominant term, yeah. And as you see that here, 1 minus gamma, 1 minus gamma, 1 plus 1 minus gamma, and this one is gamma plus 1 minus gamma. Okay, beta alpha, these come from here, yeah. Yeah, and the structure is absolutely the same, yeah. So this 1 plus 1 minus gamma, and this is gamma plus 1 minus gamma. Yeah. So in this manner, this way, we see better this. In fact, so after this, we can generalize all of this story to the case of higher order hypergeometric functions, or that is curves, algebraic curves that may correspond to periods of some other more complicated algebraic variety. And this story holds, let us say, roughly speaking, this analytic continuation procedure that this part to this part, yeah. And in this manner we get global monodromy, and we can get this somehow yeah, this kind of correspondence from Marin Barnes integrals to monodromy matrices obtained as den twist. Yeah, maybe I may propose you to. Yeah, for example, this kind of example, I'm thinking. Yeah, one question from mirror symmetry. So, periods of an algebraic variety, about a fine algebraic variety, algebraic fine algebraic variety that is hypersurface, simply. I consider it in an algebraic torus, not in Cn, but rather equals 0. It's kind of K, it is embedded into a dimension K torus, algebraic torus. Consider this. And this has Iz period equals foreign type of up to constant. To the power k times some, no, in fact it depends on phi, or how shall I say, j, maybe j, ds, the j's. The j runs from how many? Yes, in fact there are k such kind of integrals to consider, and all of them. So VJS and so this Marin boundary integral satisfies this kind of hypergeometric Pohama IJs. Okay, and then z power k minus z k theta z plus 1, etc. k theta z plus k. K. Yeah, this kind of fact. So, so phi j's, for example, in choosing phi j, as you see that it has poles. Where does this integral has poles? On the structure is the following. On the right hand side, we have 1, 2, and etc. So we have 0 and 1, 2 kind of poles. That comes from this part, and negative with negative real part pole poles with negative poles are these. So it is 0, of course, and 1 over minus k plus, in fact, some negative, non-negative numbers, and minus 2 over k plus, yeah, this kind of. So I have a family of, so if I add minus 1, 0 minus 1, it will be minus k over minus k, minus over k, isn't it? So it is enough to consider k minus 1 over k as a family. So these are somehow analogy of alpha betas. We had only 2 alpha beta. Here I have k alpha beta parameters. And so if so phi j is of course as a periodic function, and in making use of in choosing special PJS, yeah, we can erase, for example, this, make something like this: gamma s k gamma ks times, in fact, its sign gamma 1 minus s times gamma s equals sine pi s over pi, isn't it? So to get gamma to the power s, I need to multiply pi over sine pi s, and also e to the power k minus pi minus or plus pi I, so that it be a periodic power k. Times z z minus s ds. So for example, this integral, yeah, maybe I need to leave one. Somehow I want to get k, yeah, m factorial times k m factorial. This kind of solution. This kind of represent holomorphic period that is holomorphic at z equals 0. Yeah. And others can also be and over C. Over C, we can get so in fact this will give us h k minus 1 x z over C. Yeah. Yes, this will correspond to his choice of periodic functions, or linear independent solution to this hypergeometric equation that is satisfied by all periods. All periods. So I don't think that this even for this case, this work has been done. Yeah. So I propose you to do for as a homework, kind of. Yeah, in the case of k-cos 3. So on Wednesday at 1 o'clock at 211, Wednesday, the day after tomorrow. Wednesday, the day after tomorrow, 211, there was a talk given by Victoria on somehow, this kind of K0 dB P2. So derive the category of coherent sheaves on P2. It is O1, O2 generated by these exceptional connections, and after mirror symmetry, there must be some cycles, homological cycles H1 of exactly this case. Exactly this K goes, I think 2. Yeah, K goes 2 case. Yeah. So H H0 H1 H2 somehow, and this has some there will be braid monotone action somehow. Action that is studied by Beilinson so many years ago. Yeah, yes. And but this part, yeah. So full correspondence has not been yet established. It seems that I want to clarify. So if you are curious, you can come on Wednesday at 1 o'clock. You can follow the talk by Victoria Shvaryova. Yeah. It is quite, so it's a by mirror symmetry. By mirror symmetry, our story, her talk will be related to. So, shall be made. There shall be mirror correspondence, yeah, between this story and her story, yeah. And to achieve this, for the simplest way is to study this kind of Berim-Banda integral, yeah. Okay. Maybe, yeah. Yeah, K equals 3 case, for example. Yeah, kind of. It is quite easy. No, so third of the differential equation, and you calculate the monodromy and somehow. And yeah. So next time, when shall we? Next week, 27th. 27th. No, there is an exam. So, but okay, 27th. On 27th, I will talk about. I will explain arithmeticity of hypergeometric. Hypergeometric group. Now, where is it? It has been generated by two. These. I will use this representation when it is arithmetic and GL SL2. So in the case when these are integers, so these are 2, 1 to 1. So no, sorry. Alpha, beta, gamma, all of them are rational. And there is a very beautiful picture on this, how it related there, the hyperbolic geometry. In this case, Schwarz-Christoffel, Gauss-Schwarz theory. Yes, sure. Yeah. Now this is very, very beautiful, and somehow it must be at the very source of different kind of mathematical structure, like homogeneous space, symmetric space, and so on. Yeah. So I think that it is useful to see that how it looks like with this very simple example, and of course there. Okay, so did I stop here?